Hello, welcome in video 30 in the lecture Advanced Mathematic Modeling. So in the last video I showed you this crazy example of a random walk which I just came across, and I thought this fits so nicely in this lecture, so I want to share it with you. It was maybe not so well prepared, but it was just something to raise your ideas, and I think we will treat this in more detail in an exercise. Okay, so now let's continue what I started already in the last video. So we had this example of a biased random walk, so where we have increments plus or minus depending on q. And now we make a slight twist. So we go over to a correlated random walk, and it will be a random walk with a short-term memory. And these are kind of more trivial examples of random walks. And and this is, as you see, it will be very similar as in the biased random walk. So how do we do it? So now we have again our increments of the random walk, and then we take again a biased coin, and with probability q we have now an increment in the next step which is exactly the same as the increment before, and with 1 minus q we just take the negative. So this means then the next increment is just minus the increment before. So it's similar in the biased walk. The increments were just always plus or minus depending on q. And now here we say with q we repeat the last step, and with 1 minus q we go in the opposite direction than in the last step. So now when we have such a process, it's always a good idea to start with simulating some examples. And so maybe let's do this. So we could maybe I do this here. So let's say we have q equal 1, and what does this mean? Then let's say now it depends what are the increments. Now it depends, like if the first increment was 1 plus 1, then all other increments are the same. So all other increments are plus 1. And if the first increment was negative, then also all further increments are negative. We call something like this persistence. Persistent. So the increments always are the same. Now, of course, if q is not 1, but a large number smaller than 1, then of course you can have changes. You have rarely, but on some occasion you have a change between plus or minus 1, but then you're still persistent. You have a long row maybe of minus 1s, and then you jump to the plus 1s, and you have a long row of plus 1s, and so on. So if q is a bit smaller than 1, it's nearly persistent. Now if q gets even smaller, and if q is 0.5, and then we have our typical uncorrelated random walk, because then it's just a throw of a coin. It's just with the same probability we go to plus or minus. Then it doesn't really depend on the previous step because the probabilities are 0.5. So this would be uncorrelated. And maybe here to make a picture. So meaning, like if we have q equal 1, this means either over time, and now I directly plot the random walk. We start at 0, and then the random walk increases always in time, because we always have an increment plus 1. Or we go always in the negative direction, because we had here -1. So for q equal 1, we have two possible outcomes, which are persistent. So we have actually ballistic movement. So that's not diffusive very clearly. The movement is just continuing in time. But which of these two movements will be realized depends on the very first. Now if q, so that would be here q equal 1. And if q equals, for example, 0.99, then we have something like this. Then it doesn't, on average, the behavior doesn't depend anymore on the initial value, starting value. So maybe we start with +1, we go a long time up. Then maybe we have a jump here, then we go a long time down. We have another jump, we go up again. So we have intersections of increasing and decreasing walks. For 0.5, we have the normal thing that we have seen very often. We just have our normal random walk, uncorrelated random walk. What's happening if q is smaller than 0.5? Q equals 0, and this is then anti-correlated. Because what's happening now, if we start with +1, now q is 0, so we always invert the sign. Then the next increment is -1, the next increment +1, -1, and so on. So the increments are an alternating series of plus and minuses. And then if we sum them up, and we want to know the position of the walker as a function of time, yeah, then we always go up and down. So this is then anti-correlated, yeah, and the walker doesn't proceed at all. Yeah. So you see in this case here, the walker in a single trajectory can increase a lot. Here we have the normal diffusive behavior, and here in the anti-correlated, the walker doesn't move at all. So now but the question is now what happens, or let's first make a plot now of what we expect for the mean square displacement. Yeah. So we want to know over time, we directly make a double logarithmic plot. What's the logarithm of the square root of the expectation of the second moment? That's an expectation of x squared. Yeah? And so for q equals 0.5, we know exactly what's happening. So we increase here with the slope. So that's q equal 0.5, and we have a straight line with a slope 1/2, yeah, because that's the diffusive behavior. Now for the q equal 1 case, we have something different because we go ballistically. This means we go for q equal 1, we have a ballistic moment. So the typical distance that the walker achieves as a function of time goes linear with time, and in this case here we have the slope 1, here we have the slope 1/2. And what's happening for q equals 0? For q equals 0, the walker doesn't proceed at all. So for q equals 0, we go here. Maybe I do this in color so it's more easy to see. So that would be q equal 0. And so this would lead you to the idea, okay, so this diffusive behavior we have only for q equal 0.5. For q equal 1 we have ballistic, and here this. So if you now ask what happens for intermediate values of q, or for other values of q. And then if you see such a plot, the intuition would say, okay, it's very clear. I mean, so like for every q we make here a straight line, and the slope will be something in between. But you would see this would be wrong. Yeah. Then we would say, so like for example, if q is larger than 0.5, we would have here a straight line which has something in between, and then we would have a motion here which is not diffusive anymore. So this means this simple random walk would already go out of our universality class, because the mean squared displacement would then, if we have here a straight line, would go like a power law with an exponent which is not 1/2, so it would not be diffusive anymore. Yeah? And so to see what's really happening, so we have to make the calculations. And again, that's your danger when you see 3 such lines. You think you know already everything in between. And probably if you would have asked me without further analysis, I would say yeah, obviously. But here you will see the first intuition is not really correct. So let's do the calculation. So and for the calculation, we start to calculate the moment of our increments. So we want to know what's the expectation value of the increments. So and then we can see, I mean, we either invert the previous one, or we just keep the previous one, and then so you see in average the expectation value of the increments is 0. Here maybe, I mean, you can think a little bit about this if I say it's so trivial, so easy. For example, in this case, I mean, in this case, of course, the increment, the trajectory depend on the starting value. So this means we have also to average over both possible starting values, and then we need the additional information that both starting values we take with the same probability, and then you will see on average also here the expectation of the increments is 0. Yeah? Okay, so it's an unbiased random walk. So the expectation of the increments are 0. The second moment obviously equals 1, because we just have plus or minus ones. Yeah? So these are clear. Now the question, what's happening with the covariance function? So we want to know what is ei times ej if I is not equal j. And so let's, in order to see this, let's calculate first this covariance when we have this expectation value when we go one step in the future. So what is the expectation of an increment ei times the increment one time step in the future? And we do this by hand, so we see what's all possible cases. So with probability q, here, both increments have the same sign. This means we have to multiply by 1, because either both are 1, then we have 1 squared, or both are minus 1, and minus 1 squared is also 1. So that's with probability q. And with probability 1 minus q, the two have opposite signs, and it doesn't matter if ei is plus or negative, the other has the opposite sign, and if we multiply them we have minus 1. And so this is, if you work this out, this is 2q minus 1 here. Actually this is and it's funny, so like this is something we had in the last exercise, or like in the biased random walk also, 2q minus 1, but here it was the expectation of the increments, but we came across the same function, so we came across this term q minus 1 as a function of q, let's so we can plot this here also, and this appears not so often. I give this a name alpha, and so we can make here this graph again. So here the graph, and so you see, we see also again, we see if q is larger than 1/2, so we have positive alpha, otherwise negative alpha, and this will be important later if alpha is positive or negative, if we are rather in this kind of in the rather persistent or rather in the anti-correlated regime of the walk. And okay, so we know what's happening to the expectation if we go one step in the future. Now what's happening if we go 2 steps in the future? So like here, see, this is 0 steps in the future. This is just the second moment. That's 1 step in the future. Now go increments which are separated by 2 steps in the future, I plus 2. And again, we have now to see what are all the cases that are possible. And now you can maybe make the following figure to see how this works out. So let's say we start here. Let's say the first increment would have been positive. So that's a positive increment. Then with probability q, we go again upwards, and with probability 1 minus q, we go down. Yeah. And now we can again with q go again upwards, with 1 minus q, we go down. And in this case, oh, I should have stopped here. If we went down with 1 minus q, then we can go with probability q, we go up again, and with probability 1 minus q, we go 2 times down. Okay. So you see that's kind of a binomial process if you want to continue further. And so what's happening? So like with probability q squared, yeah, so we have the same sign as before, and so we multiply both of them and we end up with a +1. And then with probability q times 1 minus q, we once leave the sign of the increment and then we invert the sign of the increment. And since we have one inversion, so we have to have a -1. And this was the case of first q and then 1 minus q, but we could also have first 1 minus q and then q, which gives the same number, so we have factor 2 in front of this. And then we have, with probability 1 minus q squared, we invert the sign 2 times. Here, 2 times inversion gives again the same sign, and so we multiply with the +1. And now you have to work this out, and then we see this is 2q minus 1 squared, so it's alpha squared. And now you can do the same kind of calculations for larger time distances, and so we have ei times ei plus a time difference p, and then if you follow this up, you will get a binomial series. So we have to sum over t equals 0 until p over t, then q appears p minus t times, then we have 1 minus q, which appears t times, and then we have t inversions of the sign, so we have -1 to power t, but that's a binomial sum, and so this is just 2q minus 1 to power p, so it's alpha to power p. Right? So now we have calculated the correlation, the covariance function for an arbitrary time difference p. So maybe let's write this down. So we have our auto covariance function, and I don't remember how we called this when we had introduced the stochastic processes. We looked at this function. So now I call it C, B covariance. It depends on the time difference, and so it's the expectation of the increment at a certain time times the increment at a time shifted by k. Yeah. And this is just our parameter q here, alpha to power k. So we see actually this is an exponential function, or maybe I should have written it here, so you can write it as e to ln alpha times k. So you see the autocovariance. Actually it's also the autocorrelation, because the means are all zero, so it's the autocorrelation function also, and this decays exponentially. And so we can make a plot for this function. Let's plot our autocorrelation, and so here that's our time k, that's our autocorrelation function. So when k equals 0, this means we have here our second moment, that's just 1. So it's alpha to 0, it's just 1. And now we go down with our discrete steps, and so we have a function which is decaying exponentially. So we have an exponential decay of the autocorrelation. This means increments in the future, certain steps in the future, are correlated weakly with the increment at the first time step. Yeah? And this decay is exponential in time. And this is then what we call a short-term memory. Because we said, like, remember in our independent random walks, the autocorrelation function was, we had here at k equals 0 a certain value, and for all other k values the function was decayed already to 0. Here it was a certain value, and then it was 0 always. And now we introduced a process where we have a memory, so the autocorrelation is not 0, but it decays, and it decays exponentially. And exponential function is a very sharply decaying function, so it decays very fast. After a short time the correlation is basically 0. So we have a memory which has only a certain finite time width, so it's a short-term memory, right? But it's our first process that we introduced which has a memory. But and now if you have were careful, you said, oh, that works only for positive alpha. You're right, so this is for alpha which are positive, meaning for q's which are larger than 0.5, because if alpha is negative, then we have we get also negative autocorrelations or autocovariances. So let's plot this for negative alpha. Again, here we have the time difference k. We plot our autocorrelation function. We start again at 1 at k equal 0. And now we multiply with the with a negative function to k. So on the next time step we have a negative expectation value, then something like this. But on average the absolute value is decaying. So we have autocorrelation function which is here alternating but still decaying on time. Yeah? So it's again a short-term memory because the absolute value of the autocovariance function is decaying. So this is alpha is negative. And so this the tendency, so autocovariance functions might either decay like this or they might oscillate around 0. Yeah? And always when we go to negative, it's a sign of this anticorrelations. Yeah? And anticorrelations mean that we always go back. So there's a tendency to invert what you had done before. So, but basically, so we have now for the simple example that we had here, this was the example where the next step depends on the previous step. Yeah. So we are now we're able to calculate our moments, or the moments of the increments, first and second moment, and the covariance function. And now with this information, with this covariance function, now we can start to look what's happening to the position of our walker. And since this video is already getting long, I will do this in the next video. For the moment, thank you.